A metal well casing, in the context of electrical grounding, could potentially be considered a grounding electrode. The National Electrical Code, or NEC, dictates requirements for grounding electrode systems, and understanding if a metal well casing falls under the category of a plate electrode is crucial for ensuring electrical safety and code compliance. Let's delve into the specifics. Firstly, what constitutes a grounding electrode? A grounding electrode is a conducting object that establishes an electrical connection to the earth. Its primary purpose is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. This protective action minimizes the risk of electrical shock and prevents equipment damage. The NEC recognizes several types of grounding electrodes, including rod electrodes, pipe electrodes, plate electrodes, and ground rings, as well as other approved electrodes. Each type has specific installation requirements and performance criteria outlined in Article 250 of the NEC. Now, focusing on plate electrodes. A plate electrode, as the name suggests, is a metal plate buried in the earth to serve as a grounding electrode. According to the NEC, a plate electrode must have a surface area of not less than 2 square feet exposed to the surrounding soil. The typical material used for plate electrodes is iron or steel, and they are often copper-clad to enhance corrosion resistance. The plate must be installed below the permanent moisture level, typically at a depth of at least 30 inches below grade. The NEC also specifies requirements for connecting the grounding electrode conductor to the plate electrode, ensuring a secure and reliable electrical connection. Let's consider the question of whether a metal well casing can be classified as a plate electrode. In most cases, a metal well casing is a cylindrical structure rather than a flat plate. This difference in geometry is a significant factor. While a well casing is indeed a metallic object in contact with the earth, its primary function is to provide a structural support and conduit for accessing groundwater, not to serve as a dedicated grounding electrode. The NEC permits the use of underground metallic water pipes as grounding electrodes under certain conditions. However, this allowance typically applies to the continuous metallic water pipe system within a building or premises, not necessarily to the well casing itself. The key distinction lies in the intended purpose and the extent of the contact with the earth. A water pipe system is usually extensive and interconnected, providing a substantial grounding path, whereas a well casing is more localized and primarily serves a different function. Regarding the resistance requirement of 25 ohms or less, this criterion applies specifically to rod, pipe, and plate electrodes. If a single rod, pipe, or plate electrode is used, the NEC requires that its resistance to ground not exceed 25 ohms. If the resistance exceeds this value, the grounding electrode system must be supplemented by an additional electrode to improve its grounding performance. This requirement is intended to ensure that the grounding electrode provides an effective low impedance path for fault current. Now, let's address the issue of whether a metal well casing inherently meets the 25 ohms resistance requirement. The resistance to ground of a metal well casing depends on several factors, including the soil resistivity, the depth of the casing, the diameter of the casing, and the presence of any cuttings or corrosion on the casing surface. In many cases, the resistance of a metal well casing to ground may exceed 25 ohms, especially if the soil is dry or rocky, or if the casing is not in good contact with the earth. Therefore, it is not safe to assume that a metal well casing automatically meets the NEC resistance requirement for grounding electrodes. To determine the actual resistance to ground of a metal well casing, it is necessary to perform a ground resistance test using a ground resistance meter, also known as a ground tester or earth tester. This instrument measures the resistance between the grounding electrode and the earth, providing a quantitative assessment of its grounding performance. The test is typically conducted using a 3-point fall-of-potential method, which involves driving 2 auxiliary ground rods into the earth at a specified distance from the electrode under test and measuring the voltage drop and current flow to calculate the resistance. If the ground resistance test reveals that the metal well casing exceeds 25 ohms, it may be necessary to supplement it with an additional grounding electrode to comply with the NEC requirements. Common supplemental grounding electrodes include ground rods, ground plates, or ground rings. These supplemental electrodes should be installed in close proximity to the well casing and bonded to it using a suitable grounding electrode conductor. It is important to note that the NEC also requires that all grounding electrodes be bonded together to form a unified grounding electrode system. This bonding ensures that all electrodes are at the same potential, minimizing the risk of voltage differences and circulating currents. The bonding is typically achieved using a grounding electrode conductor of appropriate size, as determined by NEC Table 250.66. The grounding electrode conductor must be securely connected to each electrode using approved bonding methods, such as exothermic welding, listed connectors, or bolted clamps. In summary, while a metal well casing can potentially serve as a grounding electrode, it should not be automatically assumed to meet the requirements for a plate electrode or the 25 ohms resistance threshold. A thorough evaluation of the well casing's grounding performance is necessary, including a ground resistance test to determine if it complies with the NEC. If the well casing does not meet the requirements, it must be supplemented with an additional grounding electrode and bonded to other grounding electrodes in the system. Always consult with a qualified electrical professional and adhere to the latest edition of the NEC to ensure safe and code-compliant grounding practices. Grounding electrode systems play a vital role in electrical safety, and proper installation and maintenance are essential to protect people and property from electrical hazards. Understanding the intricacies of grounding electrode requirements is crucial for anyone involved in electrical work. The NEC provides detailed guidance on grounding electrode systems, and it is important to stay up to date with the latest code revisions. Here are some key considerations regarding grounding electrode systems. Firstly, the type of grounding electrode used should be appropriate for the site conditions. For example, in areas with high soil resistivity, multiple ground rods may be required to achieve the desired resistance to ground. Secondly, the size of the grounding electrode conductor must be adequate to carry the available fault current. The NEC specifies minimum conductor sizes based on the size of the service entrance conductors. Thirdly, all grounding connections must be mechanically sound and electrically conductive. Loose or corroded connections can increase resistance and compromise the effectiveness of the grounding system. Fourthly, the grounding electrode system should be periodically inspected and tested to ensure its continued performance. Ground resistance tests should be performed at regular intervals to verify that the resistance to ground remains within acceptable limits. Fifthly, any modifications or additions to the electrical system should be carefully evaluated to ensure that they do not negatively impact the grounding system. For example, adding a new circuit may require an upgrade to the grounding electrode conductor or the addition of a supplemental grounding electrode. The NEC provides comprehensive requirements for grounding electrode systems, covering all aspects of installation, bonding, and testing. Consulting with a qualified electrical professional is always recommended when dealing with grounding electrode systems, as improper installation can create serious safety hazards. Remember, a properly designed and installed grounding electrode system is essential for protecting people and property from electrical shock and fire hazards. Therefore, it is crucial to prioritize grounding safety and adhere to the NEC requirements at all times. The NEC defines the grounding electrode system as the interconnected set of grounding electrodes that are present at a building or structure. This system typically includes various types of electrodes, such as ground rods, ground plates, metal water pipes, and building steel, all bonded together to create a unified grounding path. The purpose of the grounding electrode system is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices. The NEC specifies detailed requirements for the installation and bonding of grounding electrodes to ensure the effectiveness of the grounding electrode system. One important aspect of grounding electrode system design is the concept of the grounding electrode conductor. The grounding electrode conductor is the conductor used to connect the grounding electrode to the equipment grounding bus or terminal within the electrical panel. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors. The grounding electrode conductor must be sized to safely carry the maximum available fault current. Another important consideration is the bonding of different grounding electrodes within the grounding electrode system. The NEC requires that all grounding electrodes be bonded together to create a common ground potential. This bonding minimizes the risk of voltage differences between different electrodes, which could create a shock hazard. The bonding is typically achieved using a bonding jumper, which is a conductor that connects the various grounding electrodes together. The size of the bonding jumper is determined by NEC Table 250.66. In addition to the bonding of grounding electrodes, the NEC also requires the bonding of metal water pipes, metal gas pipes, and other metal structures within the building. This bonding ensures that all metal parts are at the same ground potential, minimizing the risk of shock hazards. The bonding is typically achieved using bonding jumpers connected to the grounding electrode system. The NEC also addresses the issue of grounding electrode system resistance. As mentioned earlier, the NEC requires that the resistance of a single rod, pipe, or plate electrode not exceed 25 ohms. If the resistance exceeds this value, the grounding electrode system must be supplemented by an additional electrode. The NEC also specifies requirements for the location of grounding electrodes. Grounding electrodes must be located as close as practicable to the service entrance. They must also be protected from physical damage. The NEC also addresses the issue of underground metallic water pipes used as grounding electrodes. The NEC permits the use of underground metallic water pipes as grounding electrodes, but only if certain conditions are met. Firstly, the water pipe must be in direct contact with the earth for at least 10 feet. Secondly, the water pipe must be electrically continuous. Thirdly, the water pipe must be supplemented by an additional grounding electrode, such as a ground rod or ground plate. The NEC prohibits the use of aluminum grounding electrodes in direct contact with the earth. Aluminum is susceptible to corrosion when exposed to soil, which can compromise the effectiveness of the grounding electrode. The NEC also prohibits the use of grounding electrodes that have been painted or coated with non-conductive materials. These coatings can impede the flow of current and reduce the effectiveness of the grounding electrode. The NEC provides detailed requirements for the installation of grounding electrodes in concrete encased electrode systems. A concrete encased electrode system, also known as a UFA ground, is a grounding electrode that is encased in concrete. These systems are often used in new construction to provide a reliable grounding electrode. The NEC specifies the minimum size and length of the grounding electrode, as well as the minimum concrete cover. The NEC also addresses the issue of grounding electrode systems in high-rise buildings. In high-rise buildings, it is often necessary to install multiple grounding electrode systems to ensure adequate grounding protection. The NEC specifies the requirements for the location and spacing of these grounding electrode systems. The NEC also provides guidance in the selection and installation of surge protective devices, or SPDs. SPD are devices that protect electrical equipment from voltage surges such as those caused by lightning strikes. SPD are typically connected to the grounding electrode system to provide a low impedance path for surge current to flow to ground. The NEC also addresses the issue of grounding electrode systems in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present. The NEC specifies special requirements for grounding electrode systems in hazardous locations to minimize the risk of ignition. The NEC also provides guidance in the inspection and testing of grounding electrode systems. Grounding electrode systems should be inspected and tested regularly to ensure their continued effectiveness. Ground resistance tests should be performed to verify that the resistance to ground remains within acceptable limits. The NEC is a complex and comprehensive document, and it is essential to consult with a qualified electrical professional to ensure that grounding electrode systems are installed and maintained in accordance with the code. Improper grounding can create serious safety hazards, so it is crucial to prioritize grounding safety at all times. A qualified electrical professional can assess the specific site conditions and recommend the appropriate grounding electrode system design. They can also perform the necessary inspections and tests to ensure that the grounding system is functioning properly. Grounding electrode systems are an essential part of any electrical system, and it is important to take them seriously. By following the NEC requirements and consulting with a qualified electrical professional, you can ensure that your electrical system is safe and reliable. The information provided here is intended for general educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrical professional before making any decisions about electrical systems. Electrical work can be dangerous, and it is important to take all necessary safety precautions. Always de-energize circuits before working on them and use appropriate personal protective equipment. Remember, safety is always the top priority.